we've been on this section for a minute, and at least I can conclude it today. Oh, I got the wrong date in here. Okay. Happy Groundhog Day, everyone. I guess it kind of feels like that with this section. I'm still on LU. All right. So, a quick summary of what we've seen. So if one solve A equals B, and you're able to form Gauss elimination without row interchanges, then you end up doing A equals LU. That's what Gauss elimination produces. And then you solve Ly is equal to B, where L is a unit lower triangular matrix. So you can solve the system by forward substitution very quickly. And then you solve Ux is equal to Y by back substitution, since U is upper triangular. But what we really should do is perform pivoting in row interchanges for two reasons. The reason it comes up in the class like Math 326, avoid dividing by zero and your multipliers, we have zero diagonal elements, and to try to contain growth of round-off error. And two schemes that we saw is partial pivoting, complete pivoting. There are other pivoting approaches that I'll get into more in a later section, but those are the two best known ones. All right. So where I left off last time was simply explaining what these two pivoting schemes were, how they work, what are the pros and cons of using them. But what I did not address was, if you are going to do pivoting, how does the LU decomposition work? Because we want to carry out a process much like this one without too much extra expense from pivoting. So how do we do that? In a way, it kind of requires rederiving the LU decomposition, but in a way that takes pivoting into account. Okay. Oh, I guess I could have avoided doing this, but this is what I get for not remembering what's in my notes. Okay. So how the LU decomposition was obtained? You start with your matrix A, and then you're performing all these row operations, like subtracting a multiple of one row from another. And that is equivalent to multiplying A on the left by these unit lower triangular matrices. This handles column 1, this handles column 2, and so on. And the end result is the upper triangular matrix that comes from Gauss elimination. But now, here I'm going to assume partial pivoting. It's going to be too messy if we do complete pivoting. Now what happens is, before you begin, you might perform a row interchange to make sure that the diagonal entry in column 1 is the largest entry in that column. So that is equivalent to multiplying by some permutation matrix, P1, that performs the row swap. Once you do that, then you perform your usual Gauss elimination operations, subtracting multiples of rows from other rows. In this case, a multiple of row 1 subtracted from rows below it. All right, so now at this point, the first column is handled. Then you move to the second column. you want to make sure that its diagonal entry is larger than any entries below it. So that would call for another permutation matrix, P2. Then you work on column 2, then you go to column 3, and so forth. You see we have this alternating pattern. Swap, eliminate, swap, eliminate, swap, eliminate, and so on, until you get all the way to the second to last column. Now, here we have a problem, because in the LU decomposition, the matrix L comes from these matrices right here. It's a product of their inverses. Another way of putting it is this matrix right here, the product of all of these, that is L inverse. But L is all these multiplied together, and now these matrices have this interlacing going on with the permutation matrices. And matrix multiplication is not commutative. We can't just move these around so that these come together. So if we're going to get a LU decomposition out of this, it's not going to come from just taking these m's and multiplying them, or multiplying their inverses. So we have to look at this process more closely. And the funny thing about this is, I've looked at so many numerical analysis texts that cover LU decomposition, and then they cover pivoting, and then they show how to solve the system when you incorporate pivoting. But they never actually go for the details of resolving this. Like, how do you get an LU decomposition out of this when things are in the, so to speak, wrong order? So I thought, you know what, I want to try to untangle that ball of yarn. So let's do that. So I want to rewrite this in such a way that all of the permutation matrices are multiplied up front. So in other words, multiply A by all the permutation matrices, and then you multiply by something along the line of these m's. It won't be the exact same m's, but something to that effect. So in other words, what you're doing is you're performing the row interchanges up front and then working on eliminating entries. So how do I do that? So what I do here, before I have M1, P1. So here we have M1 and P1. Look what I do in between. I write P2 inverse times P2. In other words, I'm sticking an identity in there, but I'm writing it as P2 inverse P2. Now, this is where we get to one very important property of a permutation matrix. Permutation matrix is an example of what's called an orthogonal matrix. An orthogonal matrix has a property that it is invertible, and if P is an orthogonal matrix, P transpose times P is the identity. Or, if I multiply both sides on the right by P inverse, I have this relationship. P inverse is equal to P transpose, which is a great property to have, because computing the inverse of a matrix is generally a major chore. I advise at the beginning of a course, it's not something you do. It's not practical. But if it's a orthogonal matrix, there's nothing to do. You just transpose. So I can replace this P2 inverse with P2 transpose. So now I have P2 M1 P2 transpose. And I'm going to call that M1 tilde. So how do these two matrices, M1 and M1 tilde, differ? Well, what happens is, whatever row swap P2 performs, those rows are swapped in M1. But then the corresponding columns are also swapped. The result is that the matrix is still unit lower triangular. It's not the same matrix, but it still has the same structure. Now, I can understand if you're having trouble seeing why that's true. So, to help with that, and also just for fun, let's carry that out in MATLAB so you can see what happens. So what I need is a sample matrix like this M1 that I've been discussing. Now, what kind of matrix is that? It is unit lower triangular with multipliers. Actually, it's negatives and multipliers in the first column. So what I'll do is I'll just make a 5 by 5 identity matrix. Okay. And then I'm going to put multipliers in this first column. So rows 2 to the end, column 1. Now let's put random numbers in there. Now, just to make it more interesting, rand, as you may know, generates random numbers uniformly distributed in the interval 0, 1. I like to have a mix of positives and negatives, so I'll multiply by 2 and subtract 1. So now we're distributed between -1 and 1. The rest of this column below the diagonal has 4 entries, so that's why I want a column vector of length 4. So now I have, this is an example of what M1 could look like. So these happen to be the multipliers that are used to eliminate subdiagonal entries in column 1. So now let's suppose I want to swap rows 3 and 5. So I need to make a permutation matrix that will carry out that swap. Okay. So first, I'll make an identity matrix. And then I will make B2 by swapping rows 3 and 5 of this identity matrix. The way I can do that is I will assign rows 3 and 5, all columns, to be rows 5 and 3, all columns. So that does it. So if we take a look, what is it? Oh, supposed to be P2. Well, I'll be editing that diagram later. Okay, so here it starts out looking like the identity, first 2 rows. But you see rows 3 and 5 have been swapped. So this is the permutation matrix I'm looking for. I should point out that in Gauss elimination, the permutation matrix Pj swaps. Oh, you know what? I should not have done that. Okay. Wow, mistakes all over the place. It has to swap row J with a row I that's greater than J. So I goofed here. I need to remake this. I need to work with row 2. Okay, and I'll clean up the diary after. So it's clear and to erase evidence of my mistake. Sorry, mistakes, plural. Yay. You stay in now. Alright, so now I have a permutation matrix, a kind of matrix that would pop up in this situation. So now, if I go back to my notes, I have all these ingredients I can form this matrix. And what I'll do is I'll form it one step at a time. So M1 tilde is equal to, so first I'll perform a row swaps. So go ahead and do that. Okay, now if I look at M1, okay, 0.6, 0.8, minus 0.7, 0.8. These two entries got swapped. Now that's what we wanted, but look what happened here. Of course, when you swap the entire row. So the unit lower triangular structure got destroyed. Now, I will multiply by P2 transpose on the right, and that is going to swap columns 2 and 5 because I'm multiplying on the right. So you can see here, if I interchange these two columns, well, just by looking at what we have here, what's going to be the result of that? Well, what kind of matrix will we get?
Ask that again.
What kind of a matrix, once I swap columns 2 and 5 of this matrix, what type of matrix, like structure, what kind of matrix will I get?
Back to, I guess, lower.
Yeah.
Triangular, yeah.
Yeah.
Unit lower.
Well, let's go ahead and carry it out. It's unit lower triangular.
Mm-hmm.
Now, here's a key point here. The reason we're doing this is we want the multipliers to be rearranged. Here's why it works, because multipliers are in column 1, but columns 2 and 5 are swapped. There are larger indices. So in general, MJ is acted on by permutation matrices PK and PK transpose for K greater than J. And I spelled it out there to give it emphasis. That's why you can be certain that after you multiply by PK on the left, and you're messing with the multipliers as you want to, and then throw off the structure, when you multiply by PK transpose on the right to fix it, it will not affect where the multipliers are. That column will always go untouched because of that. That's an essential property here. So you can see here from this example, what I mentioned here, that this unit lower triangular matrix acted on by these permutation matrices in this manner is still the unit lower triangular. So this one has the row swap taken into account. Questions up to this point? So now what do we do with that? So now M1 tilde, all I've done is I've replaced this expression with M1 tilde. So now I have two permutations front-loaded. P1 was already here, now P2 immediately follows it. And then I have all the other stuff. So that's a start down the right path. And I want all the P's to happen first. But now I have to continue the process. So I use the same trick. Here, I introduce identity and insert a P3 transpose P3. And I do that here, and also here, between this M2 and this M1 tilde. So now I have two expressions of that kind. And P3 is front-loaded, as it should be. So this one, which already had P2 acting on it, now has P3 acting on it as well. But we already know that will preserve the unit lower triangular structure, because it's acting on columns greater than 1. Same thing over here. This will preserve the unit lower triangular structure. So, if I were to keep going, you can see how this is going to unfold, that I can use this idea repeatedly to shuffle all these permutation matrices all the way to the right. And this is what I have. In the general case, I have A with all the row swaps carried out first, followed by multiplying by the elimination matrices. Now, how these elimination matrices relate to the original ones, here's the original, and look what happens. All permutation matrices are applied from the one immediately following J to the very last one. And that'd be a real pain to verify, but that's how it plays out. So as a column is worked on, all subsequent row interchanges are applied to its multipliers. And only the multipliers, because these clean up the other columns. And because of what I've shown you, you can see that this is also in lower triangular. So now we have this product of consecutive unit lower triangular matrices. And now we can work with this in the same way as in the previous case where there's no pivoting involved, and form L from these. So I can multiply both sides by the inverses of these to move this over here, and this is what I get. Instead of A equals LU, I have PA equals LU, where P is the product of all of these permutation matrices that form row interchanges. So now, so really we said that with a modified LU decomposition. It's not, so the LU decomposition of A may very well not exist. So in that case, or if computing it without pivoting would lead to too much rounding error, we can form row interchanges and then get the LU decomposition. So questions about how this came about? Now, there's one other technical point I've not addressed. When you're doing Gauss elimination, as you go from column to column, you don't know in advance what rows you're going to have to swap. Because you can figure out what you want to do in the first column if you need to swap anything there. But until you eliminate entries in the first column and update the rest of the matrix, you have no idea what swap is going to come to handle entries in column 2 or column 3. That information is not known up front, which is kind of weird because here it looks like we somehow know these up front, apply them to A, and then do all this. So in a practical implementation of Gauss elimination, which you're going to carry out in one of the homework problems, and I'll talk about that later, as you make a row interchange, how do you make sure that the multipliers are stored in the right place? Because, for instance, suppose J equals 1 here. This works in the first column. Well, the matrix in your LU decomposition has all subsequent row interchanges applied to it. But in your Gauss elimination algorithm, you work on column 1 first, and then the row interchanges happen. You've already waved those multipliers bye-bye and you've moved on. So how is it possible to take this into account? And it turns out there's an extremely simple way to make sure it's correct. Here's how, all you have to do. As I mentioned before, Gauss elimination, or LU decomposition, the multipliers get stored in the lower triangle. So when you're eliminating the entry Aij to make it 0, in that spot within the matrix, store the multiplier. So that's your transcript, if you will, of Gauss elimination. So then, when you need to perform a row interchange, what you need to do is, keeping in mind that in the lower triangle you have multipliers, in the upper triangle that you're working on, you have what's going to be your row echelon form eventually, swap the entire rows. So that way, as you move on like from the first column, you're still going back and interchanging the order of those multipliers as needed. That guarantees that this LU decomposition is what will come out of it. So you actually are applying the permutations to your multipliers as you go to produce the correct L. All right. So from an implementation point of view, it all works out very nicely, thankfully. So all the stuff that I worked out here was just to see how it's possible to get a factorization like this. But this sort of thing, or this right here, you don't actually need to do that in practice. And it works out more nicely than that. So now here's what you do. To solve AX equals B, you perform Gauss elimination with partial pivoting. So before you work on a column, you determine if any row interchange needs to be made in that column. So you're in column J. Yes, does row J need to be swapped with some row greater than J? So effectively, you create the LU decomposition of the row interchange matrix. And you keep track of the row interchanges as you go. So then when you move to forward substitution, before you were solving Ly equals B. Now you're solving Ly equals PB. So whatever row interchanges you had to make to A, you also make to B, which makes sense. And you're applying whatever row operation to both sides. You have to do that. And then the last stage, Ux equals Y, is the same as before. So pivoting doesn't really change things all that much. You just interrupting each sweep of eliminations with these row interchanges. Make sure you apply them to the entire row, that you're applying them to your U that you're forming and your L that you're forming. You do it to both, and everything works. Questions about that? Now, I need to make a comment about storage. The permutation matrix P, as we've seen, is a matrix that is just a scrambled identity matrix. Most of the entries are 0. So for an n by n matrix, only n non-zero entries, and those are equal to 1. So you should never store a permutation matrix explicitly. It's a total waste of storage. And you don't have to. What you can do instead is, and it's something that is advisable for homework on this section. If you make a vector of indices 1 to n, so like 1:n in MATLAB, then whenever you need to swap rows of A, you also swap into elements of this vector, which we have to refer to indices. So then you can use this vector as indices into a vector matrix to scramble the rows. So for example, suppose you have a right-hand side vector B. If P is a vector of scrambled indices that range from 1 to n, then B of P gives you a rearranged vector. So, dang it. So this effectively computes PB is a permutation matrix. So again, another reason why you don't have to form it explicitly. So if we go back to MATLAB, example of this. Now it has a function for LU decomposition that performs pivoting. So I'll just make a random matrix A. Right, and then chances are it's invertible. And here's the usage of that LU function. So it has three outputs, LU for LU decomposition, and a permutation matrix P. So here it is being wasteful. It's going to return the permutation matrix as a matrix. Okay. All right. So here's the decomposition. Here's the unit lower triangular matrix L. Here is the upper triangular matrix U, the row echelon form. And in this case, we saw that a few row swaps happened. So the order of the rows turns out to be so 5, 3, 4, 2, 1. Okay. So I'm going to make a vector of those indices. Okay, so we have 5, and then 3, and then 4, and then 2, and then 1. So those are the scrambled indices. So now, okay, here's my original matrix A. If I do this, A, P vec, colon, that says arrange the rows according to these indices, but keep the columns the way they are. So that has the effect of performing just a rearrangement of the rows. And we see that the rows have in fact been rearranged. That is equivalent to if I take a permutation matrix that LU returned. That those matrices are the same. So this is how you can perform permutations, in this case of rows. You could do a column if you needed to, more in a more storage efficient way than working with a permutation matrix. What that would mean is, suppose I call LU again, but not with A, but rather a scramble scramble A. So since, in effect, pivoting has already been done, it shouldn't need to pivot again. Hopefully it won't embarrass me by pivoting anyway, but we'll find out. Sure enough, it did not need to do pivoting. So the permutation matrix in this case is identity. And if you were to compare the L2 and U2 here with the L and U from above, yeah, they are the same. So I just happen to know what row interchanges need to be made from the first run. Just went ahead and formed them up front, and then you do LU without pivoting. So to determine that no further row interchanges needed to be made. Now I want to point out swapping rows in matrices versus swapping indices in a vector. So I showed you this before. Oh, I thought I did. Oh, never mind. All right, so this has the effect of swapping rows 2 and 5 of A. But now, if I have a vector of indices 1 to 5, the rows all are in the original order, and then I want to do the same kind of thing, I can swap elements of P, but P is a vector, not a matrix. So I would not need to do column indices here. So that carries out that interchange. I'm carrying this out because this is the sort of thing that you'll be doing in one of the homework problems to implement partial pivoting for Gaussian elimination. Except that instead of hard-coded numbers, you have variables that represent indices. Any questions about what happened here? Make sure you do some mechanics of manipulating matrices in this manner. I mentioned before that I posted some hints, so you can find these in Canvas, and I just remember to make sure that they're on the external side too, in case anybody uses that. Now, some problems I couldn't think of hints to put out, but I may put them in here depending on what questions I get. So you can think of this as a living document, if you will. Okay. Of course, if there's a mistake in a problem, then I can point that out here too. Unfortunately, still finding mistakes. Dang it. I see that, as you can see, I had a lot to say about the first problem. We're trying to prove that like a product of two lower triangular matrices is lower triangular, or the inverse of a lower triangular matrix is lower triangular. I want to talk about the last problem coming up in this assignment. We're 3.2.20, where you're writing a solve AXB function that itself calls three functions: one for Gauss elimination, one for forward substitution, one for back substitution. So solve AXB does not need to do anything except call these three. And forward sub, back sub, you have those algorithms in the text. Well, actually, I did forward sub, so yes, you can use it. And back sub is from homework 1. So those two are taken care of. It's this one. Now you have a Gauss elim function from previous homework that does Gauss elimination without pivoting. So the thing you need to do for that is implement pivoting. So one thing to point out is that can help you. I suppose, in this example, suppose X refers to the portion of a column that you're examining to find the largest element in absolute value. So if you just call max of X, that will return the largest element. But here you don't really want that. What you want is to find out where the largest element is, because that will tell you which row you're going to swap with row J. And so if you call max with 2 outputs instead of 1, the first output V is the largest element of X. So that's the actual maximum value. The second output is the index where the maximum was found. So that's what you need to make use of. So that helps you determine which rows to swap. But what you need to keep in mind is when you are trying to determine which row swap to perform for column J, you are not examining all of column J. You're only looking at the diagonal on down. So you get an index from here. That is not the index of the row that you swap with row J. It has to be corrected or shifted. That's discussed here. So here we have an example. Like suppose you're working in the third column. And so you take this portion of column 3, find the largest element in absolute value, and max tells you that the fourth entry of this vector is where the largest was found. does not mean you swap rows 3 and 4. It means you swap row 3 with row 6, because you have to take into account the elements above the diagonal in determining the correct index of a row to swap with. So be careful about that. So you need to figure out in general for column J, how do you shift the index where you find the largest element to determine the correct rows to swap. Use ABS to take absolute value of any entity. I mentioned how to swap rows in a matrix, similar to swapping elements of a vector. How to apply permutation to a vector matrix when this is not an explicit permutation matrix, but rather a vector of scrambled indices ranging from 1 to n. So, I admit from the size of this hint, or collection of many hints, there's a lot to unpack here. Be sure to not overlook anything. Every little point that's made here will help you get from point A to point B. So it is kind of tedious. You're taking a Gauss elimination algorithm that you already have, and you're making really one significant change to it. You're carrying out pivoting. And that means right at the point before you start looping over I, like you're about to handle column J, and you have these nested loops the way it is now. Before you do any of that in those nested loops, those inner loops, you figure out if a row interchange needs to be made. You go ahead and make it. Keep track of it, like you're swapping indices in your vector P. So then it records all the row interchanges that have been made. And then you continue on with Gauss elimination as you have it. So you're just inserting this block of code at that point to handle the pivoting part. And your Gauss elimination function needs to return P as an output, because forward substitution needs to make use of that. You're solving Ly equals PB. So that's another little detail there. Okay. But so you'll plenty of time to look at these hints when you actually go do the assignment, which is due on the 9th. So you have a good amount of time. But this was a doozy, so I want to prepare you up front. So now that we've finally come to the end of 3.2, unless you want to check what's coming up. Okay. Oh wait, that's 2 years ago. Okay, after I have 2 class periods budgeted for the next section. I'm spending Monday on banded matrices, and then Wednesday on positive definite matrices, or symmetric positive definite matrices. Okay, there's a lot to say about both. Okay, so do we have any questions about what I covered, or homework questions? Does half of you still need to turn in the first homework? Or if this is the last thing you have today, you just want to go. Yeah, I guess I'm cheating by saying that, because that's where I'm at. Which y'all know how to track me down after questions later. So. Some of you definitely do. Actually, I think most of you do. So that's good. we're done.